Hello, everyone. We are back. It is now 10 o'clock Pacific time, 10 o'clock a.m. Pacific time. I'm Ming Chow, and welcome. Welcome back. Um, Packet Hacking Village, our mission is security education. And the series of talks, this DefCon that we have accepted, focus a lot on the fundamentals. Fundamentals on things like protocols, systems, things that people really need to understand before they really get into anything in security. And at our next talk, on our next talk, we have Roy Feng, who will speak about the Internet Protocol IP that you know of and TCP/IP.
Hey everyone, thanks for watching this video. This is actually my first tutorial video, so I hope everybody finds this useful. My name is Roy Feng. I can be reached via Twitter at LPF613. Today I'm going to be talking about the Internet Protocol, or widely known as IP. And this is the agenda of my talk. I'm going to start off with an introduction to IP, then I'm going to go into the details of the protocol, such as packets, IP addresses, and a feature called fragmentation. Then we're going to briefly look at the future of IP, which is IPv6. Then we're going to end off with the references I've used to prepare this presentation. Now, for this presentation, I'm going to assume no prior knowledge of networking of any kind. So I'm going to explain some definitions and some very foundational concepts. So what is the Internet Protocol? We cannot look at the Internet Protocol without looking at the word protocol. And a protocol is a set of rules for formatting and processing data. Now, why do we need protocols? Why do we need a set of rules? It is because we need computers to be able to communicate with each other and be able to understand what each other is saying. So, as an analogy, let's say we have two people who are trying to talk to each other, but one person only speaks English, but the other person only speaks Spanish. They don't have a common language, and when one person speaks English, the person speaking Spanish will not be able to understand, and vice versa. So we need to have a common language for people to talk to each other and for computers to talk with each other. So the Internet Protocol is a protocol used for the traversal of data over the Internet. And the Internet consists of many millions and billions of devices. And it will be problematic if we don't have a set protocol. So having the Internet Protocol defining a set of rules will allow devices around the world to communicate without any issue. And which brings me to packets. Packets is basically a unit of data transmitted using the IP protocol. The packet actually contains two separate parts. You have the payload, which is the data, and the header, which is the metadata that helps direct the data from the source to its destination. And the header contains metadata such as the protocol version, the header length, the type of service, which denotes the priority, the total length of the packet, some headers that is used for fragmenting packets that we will talk about later on, time to live, which is the number of intermediate devices that the packet is allowed to pass through, the protocol that is used by the data, the header checksum, which verifies the integrity of the header, and the two most important headers, which is the source and destination IP addresses, which tells you where the data is from and where it is being sent to. There are some optional headers. And so let's move on to IP addresses, which is arguably the most important aspect of the IP protocol. The IP address basically identifies a computer on the internet, and currently we are using a protocol called IPv4. And IPv4, just like anything on computers, is represented as binary numbers. And a binary number is a number that uses 0 and 1. The length of an IP address is 32 bits. A bit is basically one digit of a binary number, and in total there are about 4.3 billion different possibilities. There are different addresses. The actual number is actually lower due to reserve addresses and other restrictions, but this is a good approximation of the amount of available addresses. Now, binary is something that is difficult for humans to read, so we can convert it into decimal form. And when you convert into decimal form, it is grouped into 4 sets of 8 bits, and 8 bits together is called an octet. And these 4 sets of octets are separated with a dot. So, for example, 192.168.1.1 is an IP address in decimal form. Now, 8 bits gives 256 different possibilities, which is much better than if we use the bit notation, which would give 4.3 billion different possibilities. One important concept to IP addresses is subnetting. Because we have a large IP address space with 4.3 billion addresses, we need a process of breaking down the IP address space into smaller networks, and the subnet mask is used to help with subnetting. The subnet mask is the same 32-bit length as an IP address. It divides an IP address into 2 parts, the network part and the host part. The network part is represented using ones. Host is represented using zeros. The network part is used to direct packets to its destination. The process of directing packets to its destination is called routing. So let's go to a subnetting demo. So here I put together some charts that talks about the decimal number system and the binary numbering system. Let's start with the decimal numbering system, since this is something that we are all familiar with. When we count using decimal, we start from 0 and count to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And when we get to 9 and we need to add one more, we don't have any more numbers to use, so we carry over to the next digit, which gives us 10. Then we count up as normal, 11, 12, 13, 14, 15, and so on. And we can use this principle and apply it to a binary number system. In the headers, I put the number that the digit is supposed to represent. So you have 1, 10, 100, and 1000. From a mathematical perspective, we have 10 numbers, 0 to 9, so that's why you see the 10 over here as the base, and then the power, which starts at 0 for the first digit, 1 for the second digit, and so on. So if you take 10 to the power of 0, you get 1. 10 to the power of 1, you get 10. 10 to the power of 2, you get 100, and so on and so on. So we're going to apply this into binary. So I have the same headers over here. You have the base 2 powers and the corresponding decimal number. As you can see, it is much more different than the decimal numbering system. Whereas you have decimal, you have 1, 10, 100, and 1000. In binary, you have 1, 2, 4, 8, 16, 32, 64, 128, and so on. So it is something that humans don't usually use day to day. So when we count up, we only have 2 numbers, 0 and 1. So 0 and 1 still stay the same because these are the numbers that we use. But after 1, we need to carry over to the next digit where we have 1, 0. Then we count up to 1, 1. Then we need to carry over again, which becomes 1, 0, 0. Then we count up again, 1, 0, 1, 1, 1, 0, then 1, 1, 1. And on the right side, you see the decimal equivalent that that represents the binary number. So we have 0 and 1 that remains the same. 1 0 in binary represents 2, 1 1 in binary represents 3, 1 0 0 represents 4. So how do I convert from one to the other? So let's start from converting binary to decimal. Because that's much easier to understand. So everywhere where you see a 1, so the column where you see a 1, you multiply that 1 by the column heading, and then add them all together to get the decimal number. So if we scroll down and do an example for 1011, so we have a 1 here. 1 is in this column, which represents 1. 1 times 1 is equals to 1. In this column, we have a 1, and this column represents a 2. So 1 times 2, which is equal to 2. Add 1 from the previous column, then you get 3. You have a 0 and 4, so we don't do anything. Then in this column represents 8, and we have a 1 in here, so 1 times 8 is equal to 8, plus the previous 3, so 8 plus 3 is equal to 11. So that's how you get 11. So that's a very quick way to see how you can convert from binary to decimal. But how about the other way around? So let's look at 9. The way you do it is you want to find the highest header over here that can be divided into this decimal number. So in this case, it would be 8. So 8 goes into 9 one time. So you put a 1 here, and 9 minus 8 is 1, which is the remainder. And so you find the next number that can divide into 1, which is 1. 1 goes into 1 once, and with the remainder 0. So the binary representation of 9 is 1001. With the knowledge of converting between binary and decimal, now we can go on to talk about subnet mask. As you might remember, a subnet mask divides an IP address into two parts. You have the host part and the network part. The network part is represented by 1s, and the host part is represented by 0s. There are two different notations for representing subnet mask. The very simple way is the slash notation, or more formally the CIDR, or classless interdomain routing notation. And that's basically a slash followed by a number. The number tells you the number of 1s that are in the subnet mask. The other way is decimal. So you convert the CIDR representation into a decimal number. Now, the rule of thumb is for 1s that represent the network, it's always on the left. And for the host that is represented by 0s, it is always on the right. And there cannot be any mix and matching of 0s and 1s. The 1s needs to be together on the left, and the 0s need to be together on the right. So with that said, let's go to an example of subnet mask. So let's pick something relatively simple, /24. /24 is probably the most used subnet mask in networking, because you see it in corporate environments all the time. So the /24 means there are 24 1s that represent the network. So you have 8 here, 8 here, and 8 here, which makes up 24. And one thing about /24 is it is on a boundary of an octet, right? These are a set of 8, 8, and 8 bits, which makes things a lot easier. And remember that when you have 8 1s in binary, it equals 255 in decimal. So after the 1s, you have all 0s. So a /24 can be represented in decimal by 255 192.255.255.0. Now let's pick something else that's not on a octet boundary. Let's say we have a slash 26, right? So slash 26 is it consists of 26 ones in binary. So we have 24 here, 25, and 26. Now to convert this into decimal, we need to do what we did previously to convert from binary to decimal. So I also have the headers over here. So we have a 1 here, and the header here says 128. So you have 128 plus the next digit, which is a 64, and together you get 192. So a slash 26 is equal to 255.255.255.192. In fact, if you look at the entire chart here, right, you'll see a pattern. So starting here, you have 0, 128, 192, 224, 240, 248, 252, 254, and 255, right? Then once you finish that octet, you can go to the next octet where it starts from 0, 128, 192, 224, 240, 248, 252, 254, and 255. So these are the numbers to have to remember if you don't want to do the conversion manually. Let's apply to IP addresses now. So let's do a simple example. 192.168.1.1 with a subnet mask of 24. Now we know that from previously that a slash 24 consists of 24 ones. So let me fill that in right here. And the equivalent in decimal is 255.255.255.0. One important thing that we need to figure out for a network, so because this consists of a address in a single network, is to find the starting address and the ending address. So the way to do that is we need to convert this into binary, and then we need to do a little bit of math to calculate. So we use the previous method I mentioned to convert the IP address into binary. So 128 goes into 192 once with a remainder of 64. 64 goes into 64 once with a remainder of 0. So the rest are all 0 in this octet. 128 goes into 168 once with a remainder of 40. 64 goes into 40 0 times. 32 goes into 40 once with a remainder of 8. 16 goes into 8 0 times. 8 goes into 8 once with a 0 remainder. Now 1 goes into 1 once, so we can just fill this in directly. Right, so conversion to binary is done. Now, to find the starting and the ending address, what we need to do is look at the subnet mask and find the last one, right, which is right here. And everything after that is represented by zeros within the subnet mask would count as the host part within an IP address. So let me highlight this here. And to find the beginning address, what you need to do is set everything to 0. Right, so this one is an easy example. So you have 192.168.1.0, which is equal to network ID. So the first address in a network is always called the network ID that identifies a network. Then the last address is all ones. In this case, because it's a full octet, we know it's 255. So we have 192.168.1.255, and this is known as the broadcast. A broadcast is basically a communication that goes out to everybody within the network. with the same network ID. Right, so this one is simple because we have a /24, which is on a boundary of an octet. So let's try something that's not on a boundary. Let's say we have an address 172.18.21.3, for example, right? And it has a subnet mask of 21, right? So 21, a /21 subnet mask means you have 21 ones. So let's start with 16, 17, 18, 19, 20, 21. And the rest are all zeros. Right, so now let's convert the IP address into decimal. So 128 goes into 172 once, with a remainder of 44. 64 goes into 44 0 times. 32 goes into 44 once, with a remainder of 12. 16 goes into 12 0 times. 8 goes into 12 once, with a remainder of 4. And 4 goes into 4 once, with 0 remainder. 128 goes into 18 0 times, 0 times, 0 times. 16 goes into 18 once, with a remainder of 2. 8 goes into 2 0 times, 4 goes into 2 0 times, 2 goes into 2 once, and with remainder 0. For 21, we know 16 goes into 21 once, with a remainder of 5. And 8 goes into 5 0 times, 4 goes into 5 once, with remainder 1. And finally we have 3. 2 goes into 3 once, with the remainder 1, and 1 goes into 1 once. Now, using the same principle as previously, so we take all the zeros in the subnet mask and the IP, and we can now zero them out to find the first address and the last address. So let's do that here. Right, so here we have this octet with only one 1, so that's a 16. So here we have 172.18.16, and the rest are all zeros. And that's the network ID for this IP address. Now for broadcast, we turn it all into 1. Right, so you have 1 times 1, which is equal to 1. 1 times 2 is equal to 2 plus 1, which is 3. 1 times 4 is equal to 4. 4 plus 3 is equal to 7. 1 times 16 is equal to 16 plus 7, which is equal to 23. So we have 172.18.23.255, which equals to the broadcast. Right, so these are two simple examples of how to get the first and last address, which is the network ID, and the broadcast address of an IP address, and with a subnet mask. Now let's talk about IP classes. The classes of IPs actually have a historical context. It is a way to divide the 32-bit address space into smaller address spaces so that they can be used on networks. And they're divided into class A, B, and C. So in class A, it has a subnet mask of /8, an address range from 1.0.0.0 to 127.255.255.255. For class B, it has a subnet mask of /16, and an address range from 128.0.0.0 to 191.255.255.255. Class C has a subnet mask of /24 and a address range of 192.0.0.0 to 223.255.255.255. Now, if you do the calculation for the number of hosts within a class 8 address. The /8 means there are 8 ones in the network, which means the rest of the 32 bits, so 32 minus 8, which is 24 bits, are used for the host part. And 2 to the 24 is many, many millions of addresses, and this is not very, very efficient. So we stopped using this class system in order to subnet networks. That's why we use the slash notation, the CIDR, in order to subnet networks. We also have class D and E, which are special address classes, which I will talk about later. So now let's talk about special IPs. There are a number of special IP ranges that are defined. So first of all, we have the private address space, and that is defined in the RFC 1918. And these are 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. Next, we have the loopback IP space, which is 127.0.0.0/8. And a loopback is basically, well, it loops back to yourself. So it is an address that represents yourself. We have the self-assigned IP space, which is 169.254.0.0/16. Next, we have the multicast IP space, which is the class D address space. That ranges from 224.0.0.0 to 239.255.255.255. Next, we have a range of IP addresses for research purposes or for future use, and known as class E, and that ranges from 240.0.0.0 to 255.255.255.254. And lastly, we have the broadcast address of 255.255.255.255, and that is used as a general broadcast address. Now, IP addresses, especially for that are used on the public internet, needs to be managed, and we have registries to manage the assignment of IPs. So the entire address space is divided and assigned to regional internet registries, and these internet registries are responsible for the allocation and registration of IP addresses in their region. And these are the internet registries around the world that are responsible for different regions. For example, the American Registry for Internet Numbers, or ARIN, is responsible for Antarctica, Canada, parts of the Caribbean, and the US. Next, let's talk about fragmentation, which is a feature of IP. Fragmentation was built into the protocol because due to the fact fragmentation was built into the protocol due to the fact that networks are built differently around the world and may not support the speed and the maximum allowable data, or they may not. Fragmentation was built into the IP protocol due to different providers around the world using different equipment that have different performance metrics. So it has different speed and the maximum allowable amount of data, which is called the maximum transmission unit for the IP protocol. And large packets are broken down into smaller fragments if needed so that it can be transmitted. And end devices can request intermediate devices on the internet, which are called routers, to not fragment. But if a packet is larger than the MTU, the maximum transmission unit, and the end device requests not to fragment, then the packet is dropped, so it needs to send again. Now the future of IP is IPv6. We are currently at IPv4, but there is a migration to IPv6. The internet is running out of IPv4 addresses, and that was one of the main reasons of designing and moving towards a newer protocol. IPv6 was designed to replace IPv4. It has support for much longer address at 128 bits, so hopefully it is enough for the foreseeable future. It has a smaller packet header, which makes it more efficient for routers on the internet to process packets. And there are many more features in IPv6 that are out of scope for this talk. So these are some of the references that I used to prepare for this presentation. And thank you for listening. And if you guys have any questions, you guys can reach me on Twitter at LPF613. Thanks for watching and have a great day.
Roy, thank you so much. Thank you so much for your talk. Um, and I hope that this will be the start of more talks on fundamentals, which we badly need in the security field. What we're going to do is we're going to, at 2 o'clock, we have a not 2 o'clock, sorry, 2 o'clock Eastern Time, 11 o'clock Pacific. We have a very, very special talk by MITRE. And that's going to be at 2 o'clock Eastern Time, 11 o'clock Pacific.